Welcome back, students. In this session, we are going to study about the property of photons. Photon is a particle that we are coming across for the very first time. Already we are familiar with the other subatomic particles like proton, electron, neutron, alpha particles and something like that. So here we are going to exclusively deal with the photons, and we are also going to see what are the different properties that are associated with photons. Photons was first proposed by Einstein. Actually, it was not discovered or invented. He actually proposed an idea of photons. He said that the light, white light, is made up of huge number of energy packets, each of energy h mu. That was the proposal made by him. Okay, energy is not only that what we see with the light, but it is made of energy packets. Okay, each energy packet is called quanta. That is what he said. Later on, each energy packet is individually known to be photons. And you see, each quanta has a energy of h mu. Each quanta has an energy of h mu. Later on, this quanta is what we call as photon. Then the speed of light is given by the symbol small c, and the speed is later on discovered to be 3 into 10 power 8 meters per second it is. So these are all few basic informations. Then the energy of the photon is equal to h mu. Mu is written as h into c by lambda. H into c by lambda it is. If you are going to be provided with a light of certain wavelength, and if you take that wavelength and if you just substitute it over here, you will get the answer in terms of joules. But unfortunately, in this chapter, we will never deal energy with the joules. We will always try to convert it to the electron volts. So listen, h into c by E lambda, and if you rewrite all these three constant quantities, this will be written as 12,400 divided by lambda electron volts. This is what we get. So whenever you are provided with any light of any certain wavelength, all you have to just do is you have to take that wavelength and you have to just substitute in here. But please make sure that you always substitute the wavelength in terms of Armstrong unit, because I have also considered this Armstrong unit and I have calculated the whole thing. So please make sure that everything is substituted in terms of Armstrong unit over here, and if you just plug the entire value in at this place, you will end up with the energy. So this is the energy of the photon. Okay. So now what Einstein is trying to propose in here is, he is saying that the light is made up of particles, which means light not only behaves like a wave, but it also has its own particle nature. This is what he is trying to propose. Okay, that is the reason why even if we try to write the energy, I will be writing it as n into h mu. N into h mu, where n stands for the number of photons. N stands for the number of photons. Okay. So this is how the whole thing is being written in here. So now what we are going to see is how the photon calculation is done and what are the different things that we can do with the help of the photon is what we are going to see. So, this idea actually brought us to a very important experiment called as the photoelectric effect, which we will be dealing it in the next session. So, in the photoelectric effect, what I will be doing is, I will be continuing with the experiment, and with the results that we get through the photoelectric effect, I will conclude that the light is made up of particles. Okay. So, now how much amount of photon is present in a light? That is a question. Okay. So, we have white lights all around our rooms, and even when you go out there are plenty of white lights you will find. So, for a particular light, how much amount of photons are produced is what I am concerned about. You see here, n represents the number of photons, which is equal to P by E it is. P by E it is. P stands for the power. P stands for the power. E stands for the energy. P stands for the power and E stands for the energy. So, the ratio of power to energy will represents the number of photons that are going to come out per unit time. Okay. So, now what we can do is we can rewrite the whole thing and we can finish it off, which is like P by h mu, and when I cross multiply this, P is written as n into h mu. So, these are the different ways in writing the expression for the power and energy. So, now the next question will be the intensity of light. What exactly is intensity? Listen very carefully. Intensity is something associated with the brightness. Okay. Whatever I am saying now is very important, because I will be recalling the same things again when I go for the photoelectric effect. Intensity is associated with the brightness of the light. If a particular light is very bright, what I can say is the intensity of the light is high. If a particular light is very dull, then the particular intensity of the light is very low. So, now listen very carefully, where the intensity is written as I is equal to E by A into T. E by A into T. I stands for the intensity, E stands for the energy, and A stands for the area. So, if I rewrite the whole thing again, it becomes P by A, again I can rewrite my P from here as N into H into mu, by A. Here you can see that the intensity is directly proportional to N. Intensity is directly proportional to N, which means that if the intensity of the light is very high, then the number of photons that are going to come out of that particular light will also be high. Likewise, the area is inversely proportional to intensity. What exactly is the area stands for in here? When we were studying wave optics, we came across wave fronts. There we studied about two different wave fronts, if you could recall. One is spherical wave front, and the second one is plane wave front. The second one is the plane wave front. One is the spherical wave front and the second one is the plane wave front. So, depending on this, the area will be. Okay, you see, if it is going to be a point source, then the wavefront that we acquire from the point source is nothing but a spherical wavefront. And if it is going to be a linear one, okay, if it is going to be a linear one, the wavefront that we will acquire will be a cylindrical wavefront, and a part of a cylindrical wavefront will be a plane wavefront. Already we are familiar with these things, we have already done in the wave optics. If you are not so clear about this, I strongly recommend you to go back to that video to see how the wavefronts really look and work. Yes, so now I is inversely proportional to 1 by 4 pi r squared. This is for the point source. Point source will actually produce a spherical wavefront. Likewise, I is directly proportional to 1 by 2 pi r into L. So, this is the expression for the linear source. A linear source will produce a cylindrical wavefront, and a part of a cylindrical wavefront is nothing but a plane wavefront. So, if you see, in most of the cases we will always use the intensity is inversely proportional to r squared. This actually plays a very crucial role. You know what? I will tell you an experiment. You take a torch light, and if you flash your torch light close to your wall, you will see one bright circle on your wall when you keep your torch light very close to your wall. But when you move your torch light away, the brightness of the torch light on the wall keeps getting bigger and bigger. The circle that falls on the wall gets bigger and bigger as you move your torch light behind. So, that is what this means. As the distance of the source from the screen increases, the intensity decreases. Just like your Newton's laws of motion and just like your Coulomb's law, intensity is also an inverse squared one. Okay, these are very important things. You might wonder why we are actually focusing on the photon this much, because in the next topic when we go into photoelectric effect, these photons that we have studied here is going to play a crucial role. Okay, because depending on the number of photons and depending on how they behave and depending on their own energy, the whole photoelectric effect experiment is going to accordingly change. That is the reason why we are so concerned about the photons and their properties in here. Okay, so there are few things that you have to keep it in your mind very well. One is, intensity is directly proportional to the number of photons, which means if the light of brighter intensity, if the light is going to be of higher intensity, the number of photons in that will be high, one thing. The second thing is, intensity is inversely proportional to the square of the distance. Intensity is inversely proportional to the square of the distance. If you remember these two things, you can answer all the questions. And I have also seen few other questions being asked based on this formula, the power and energy. You see, the ratio of power to energy will give you the number of photons. Okay, please do remember all these formulas because it will be very helpful for you when you go for your numerical sessions. So, with this note, we come to the end of this session. In the next session, we are going to start doing the photoelectric effect. This is a very important experiment, and I will again meet you in that session. Thank you.